Okay, we're going to do some more circular dynamics, as in all of the old topics again, but in terms of rotation. So we're going to look at two new ideas. So we're going to look at momentum and energy, but we're looking at rotational versions of both of them. So let's get started. Here's a basketball, and it has a speed of 0 and it has a height of 0. So by our old definitions of potential and kinetic energy, it has no energy because it isn't moving and it isn't displaced by any height, so it's not sitting on top of a hill or anything. And I know it doesn't look like it's sitting on the ground, but let's assume that it is. So this ball is just sitting on the ground of no height and no speed, so it has no energy. Well, we're going to change one small thing, and we're going to say that it is now spinning. It still has no velocity in either direction, so it's not rolling across the floor. It's not going up a hill or down a hill. It's just spinning on the floor. Well, your intuition might tell you by our old definitions of energy that it still has no energy, but it is moving. So it is, this thing is spinning around. So it has the potential to do work of some kind. So it has to have some kind of energy. So even though it's spinning, it's not changing position at all, but it does have some kind of energy. And we call that rotational kinetic energy. Our original definition of energy depends on the mass and the speed. And I'm going to put a new subscript under that K. I'm going to put a T, and that means translational. So translational, which means it's moving in a certain direction. So if you watched the center of mass and you were measuring its position over time, it would be changing. So it would be moving across the floor. Well, now we're going to look at its rotational energy. So the equation, just like every time we've done anything rotational, it looks just like something linear, but with new letters. So I'm going to put this little subscript R, and that just means rotational. So rotation, oh goodness, rotational. There, I ran out of room. So instead of M for mass, if you think back in our last unit, we had this new idea of mass, of rotational mass, and we used the letter I, and that stood for the moment of inertia. And so that depends on the size and the shape and the mass of whatever the object is. And then instead of velocity, we're going to look at angular velocity squared. So here's our new definition of energy. So now an object can have two kinds of energy while it's moving. It could be moving translationally and have an energy, and it could have even more energy if it's doing that and it's rotating. So remember, I depends on the shape. I is the moment of inertia. It depends on the shape of the object. So I'm just going to give you this one for now so we can do an example. This is the moment of inertia for a solid sphere. A solid sphere of some radius. So if there's the center of mass, and then if that's the radius of the outside, there's our radius m, and it has some mass, and it's just a solid sphere. And it's defined, its moment of inertia is defined by this. So let's do an example of that. Here's our basketball again, and it is spinning. So it is spinning at this speed, this angular speed. It's going 20 radians per second. So I Googled really quick what the mass and what the radius of a basketball would be, of a normal basketball, so we can get a reasonable answer. And it has that mass of 0.625 kilograms and a radius of 0.124 meters. So that's like the standard size and weight, or size, radius and mass of a basketball. And my question is, what would its kinetic rotational energy be? Well, our equation is 1/2 moment of inertia times angular velocity squared. So we just need to plug some stuff in. 1/2. Okay, so our moment of inertia was 2/5 mr squared. So 2/5 times the mass times the radius squared. Now that's just I. That whole thing I wrote out there was just 1/2 of I. Then we multiply by the angular velocity squared. So when we calculate all that out, we will get what the energy of this basketball is only due to rotation. So it's not rolling across the floor, it's just spinning. And it doesn't have any potential energy either. So if I multiply all that out and I keep all of the units, I'm going to get kilogram meters squared per second squared. And if you're wondering about the radians, radians aren't really a unit, so it is like a unitless unit. I will have a better answer for you in class if you're curious about where that comes from. But for now, these are the units that we get. And the kilogram meters squared per second squared, those are joules. So it has 0.76 roughly joules, only due to spinning. Okay, so we have a new way to calculate rotational energy. So what I'm going to do now is I'm going to do a conservation of energy problem, just like some old ones that we used to do, but I'm also going to factor in the rotational energy. So get ready for a comparison, and it's a very easy comparison. We've got two objects of the same mass, the same shape, and the same size. They're two identical things, and one of them is going to be spinning and one is going to be not spinning. So the first one is the one that is not spinning at all. It's just moving, it's just changing its position over time. So it has some speed, but it's not rotating. So it has a velocity, but it has no angular velocity. Well, its energy would just be a no-brainer. That'd be 1/2 mv squared. But if we compare it to the same one moving at the same speed, but it's also spinning, so it has the same speed and it also has the same angular velocity. So we have two energies to add together. So we have 1/2 mv squared and 1/2 I omega squared. So it's pretty obvious that if something is moving at the same speed as something else and it's spinning, it has more energy because it took some energy not only to move it but also to make it rotate. So get ready for some algebra. We're going to do a long conservation of energy question. So we're going to have to make those substitutions in. So we're going to use the same shape of a sphere, and then also I'm going to show you where this comes into play. But first, let's set up the problem. So this is an easy question. If we didn't factor in anything rotating, and I wanted to know the speed at this point down here, then all I would need to know is the height that it fell from. So if it went from, oops, let me go back. Oh my gosh, stop. Okay. So if we wanted to know how fast it's going at the bottom of the hill, we would have to know what the height of the hill is. And we could use potential energy and kinetic energy because all of the potential energy there will turn into kinetic energy down here. But in this case, what we're factoring in, not only are we factoring in that it's moving across the ground, but we're also factoring in that it is, that's just weird looking. We're also factoring in that it's rotating. So it is spinning and moving this way. There's a lot of arrows right there. But anyway, so we have a potential energy that it starts with. And we know that when it gets to the bottom, there's no more potential energy, so it's just kinetic energy. If we factor in the rotation, we just have to add that into our equation. So all of our potential energy turns into translational kinetic and rotational kinetic. So let's expand all of this out into each equation. So mgh, that's one that we still know. Translational kinetic, that's the one we still know, 1/2 mv squared. And then our rotational is 1/2 I omega squared. If we make the appropriate substitutions, we can still solve for the speed, given only the height and the shape of the object. So I'm going to start simplifying this and then showing you where all this algebra comes in. So 1 half mgh equals 1 half mv squared. And then plus, now we need to substitute in I, the moment of inertia of a sphere, and that's 2/5 mr squared. So that was our given. We're going to use the same shape as the last example, and then times omega squared. We still have to do a little bit more substituting, so I'm going to rewrite that bottom line, this bottom line right here, I'm going to rewrite it on the next page so that we can have a little bit more space. So I am going to try to rewrite omega in terms of this velocity and the radius, because we know that, okay, so first of all the masses cancel. So let's rewrite that. Let's just do one step at a time here. So we've got no mass, all right, so we eliminated the mass, we don't need that. But I can make a trick, a substitution trick right here. We know that velocity, radius, and angular momentum are related to each other. So what I'm going to do is I'm going to try to substitute this into our equation. If I square that entire equation, notice how r omega squared is here and r omega squared is here. So that means this entire thing equals the speed squared, or v squared. So let's rewrite it again. 1 half v squared plus 1/5 velocity squared. Look at that. So now we can solve this in terms of v. So we just have to do a little bit more algebra. So rewriting it really quick, gh equals 1 half v squared plus 1/5 v squared. If I add those fractions together, I should get 6/10 v squared. And then I'm going to simplify that to 3/5. And then I'm just going to keep going with algebra and then move that to the other side and then eventually solve for the speed equals this. So the speed of that object, if it is at some height on a hill and it rolls down to the very bottom to no potential energy, its speed is calculated like this. Now we know what g is because that's always a constant, so we knew exactly what the speed was of this object without knowing a mass. We were only given a height. We actually didn't need the radius, so actually I'm going to cross that out. But we just knew the height and the shape. So all we were given was height and we were given shape. And then we could find the speed of that object. So let's see. All right, so let's recap all of our energy types at this point. So all possibilities of energy that we know equations for. So we now have two kinds of potential. We know that one is gravitation, so that's mgh, and we know that we have potential energy of a spring, and that's 1 half kx squared, but you can look up that equation. You don't have to memorize it. And then now we have two kinds of kinetic energy. We have translational and we have rotational. So two kinds of potential, two kinds of kinetic. All right. So I'm actually going to do this next topic in another video. So that is all for now. We're going to focus in class on some problems with some moment of inertia and energy, and being able to use energy conservation and being able to factor in the rotation of different objects.